Okay, so today mainly we will be discussing about the different arithmetic group instructions, and this will include addition, 8-bit addition, 8-bit addition and subtraction between the CPU registers, 8-bit addition and subtraction between CPU register and the memory module that is connected with 8085. Then we will discuss about 8-bit addition and subtraction between memory and CPU registers, vice versa, double addition and subtraction. Then we will talk about increment and decrement of register and register pairs. Then we will discuss and see what is decimal adjust accumulator, but the decimal adjust accumulator will be taken up in the next class. In this class we will discuss all the instructions related to this above decimal adjust accumulator. Now if we talk about addition operation on 8-bit data, now the first that is possible is addition between the register CPUs. Now we all know that there are pair of registers available in the microprocessor 8085, but they can also be used in a single manner. So if we are talking about BC register, B and C can be separately used, as well as HL, DE, and accumulator itself is 8-bit. And always remember, accumulator in this case, in most of the cases, accumulator is the by default register. Now when we talk about add R CPU, here add R CPU means the registers inside the microprocessor 8085, and it actually requires one machine cycle, that is only one read. It is the fetch of operational code. All the flags gets affected, and T state required is only 4, and then we have register, and the addressing is register type of addressing. Fine. So 8-bit register is added with accumulator and saved in accumulator itself. So here the accumulator is the default register. Now let us try to understand this using certain examples, then it will make the concept, you'll be able to understand the concept behind it. Now let us assume the first example where it is add A. So before execution add A, suppose we had a data around 02 in accumulator. Now everything mentioned here is in hex, so whatever we treat here is in hex. Now add A. Now what is add A? Add A means the content of accumulator gets added with the content of accumulator itself and is saved in accumulator. So the situation is it gets added, the same content gets added and it is saved in accumulator. So before execution the content is 02, so the 02 is again getting added with 02 and it is saved in the register accumulator itself. So you will get 04 in accumulator after it gets executed. So similarly, if we talk about add B, now let us assume that 02 is available in A and 03 is available in B. So after execution of this particular instruction, it will get added and will be stored in accumulator. Fine. Here you can see the content of accumulator is getting overwritten, but remember the content of register B remains the same. Since the default register here is A, so the content A will definitely get changed after the execution of this particular instruction. Now let's move on to add C. Similarly, the C is getting added, the content of C is getting added with A, and the result is stored in accumulator itself. So similarly, there are other possibilities like add D, there are other possibilities like add E, and there is another possibility add H, and the last one is add L. So these are the examples where the default register is accumulator and the contents of the given register gets added with accumulator and it is saved in accumulator itself. Now let's move on to the operation on 8-bit data, but we are here now interested in memory and the accumulator. So we have one instruction, it is add M. Now you have to remember this is register indirect addressing. Why? Because there is M in the instruction. So whenever there is M in the instruction, the microprocessor system will try to find out what is the content in HL, and that content in HL will be treated as the memory address. So now the microprocessor will be interested in the content which is indirectly pointed by HL. Okay, that is the memory. Now add M here will require 2 machine cycles because add M is itself is having an operational code which will be first fetched by the microprocessor. Only after the decoding of that particular instruction or the opcode, the microprocessor will be able to understand that it is the add M instruction. Then definitely it has to get the content from the memory and internally add it and save it into accumulator. So for that it will require another machine cycle. Hence, to execute add M you will require 2 machine cycles. Then you have 7 T states, and obviously the addressing mode of this particular instruction is register indirect addressing. Now let's see the 8-bit content of accumulator which is added with memory content whose address is an HL pair will be saved in accumulator. So again the default register here is accumulator. Now let's see with an example. Now you can see we have a situation where it is before execution, but in this diagram you can see the accumulator is having 0 2 and the content of HL is E000. Now the plus here means that the pointer which is the HL register here, which is pointing to a particular content in the memory, is getting added. Okay, so please don't get misguided by this plus symbol. This means the entire thing is getting the content across this particular location is getting added. So before execution it is like this. So after execution it becomes 06. Why? Because previously accumulator was having 02. Now the add M here means the content of memory gets added with accumulator whose address is in HL pair and is saved in HL. So the pointed by HL is E000. The content across this is 04, and so that 04 gets added with 02 and the accumulator content becomes 06. Now let's see if we talk about carry. Okay, so sometimes this is very important when we go with a repetitive addition type of any operation. Okay, now in this case again here we are considering the processor registers, that is all the registers inside the processor which can be used for arithmetic operation. So it will require only one machine cycle and it will affect all the flags, and the addressing is registered because the destination and source address is defined in the instruction itself, and it will require 4 T states. So in this case again, the content of the register that is mentioned gets added with accumulator, and the carry flag is also added. Carry flag status is also gets added. That means if the carry flag is having 1, it will get added. If the carry flag is having 0, it will get added. Whatever be the content of the carry flag register, that it will get added with this while this particular instruction is executed. So let's see an example. Here again we have ADCA, which means content of accumulator gets added with content of accumulator with any previous carry. So suppose the carry flag is 1 and the content of accumulator is 02, means the same thing will get added, and what we get is 05. So after execution, all these things get added and the content is reflected in accumulator. Similarly, add B, here what happens is the content of B register gets added with the content of accumulator with any previous carry. So now it becomes a 04. In this case, the content of B register is 1, CY, that is the carry flag status content, is 1, and the accumulator itself is having 02, so it gives me 04. Now similarly, if we talk about ADCC, here the C register content gets added with A and the carry flag, and we get the result in accumulator. Similarly, it is with respect to ADCD, it is similarly with respect to ADCE, and again it is similar with respect to H and L. Fine. So now let's move on to the next section. Here the AND operation on 8-bit data is with carry and with the memory. So again what is happening is, before execution of this particular instruction here means the content of accumulator will get added with the content of memory whose address is in HL pair and with the previous carry. So obviously we have a carry flag status, which is here it is given in the example as 01, and the content of the accumulator is 02, and the HL pair is pointing towards the location E000, which is having a content 04. So after adding this, what we will get is 06. I'm sorry, it should be 7. It's a slightest mistake here. So it should be actually 7. So what we get here is the result as 7. So now let's move on to the addition operation under immediate addressing mode. So in this immediate addressing mode, you can see we are interested in the data which is provided directly with the instruction itself. So in this case, we will be again having the accumulator as the default register, and with the default register the content will get added which has been immediately supplied in the instruction and will be saved in accumulator itself. So if we have if we consider an example where we have ADI 08, here the content 08, which is a 8-bit data, is directly supplied with the instruction, and this content gets now added with the CPU register, which is 02, and presently having the content 02, and it is saved in the accumulator register, which again gets updated, and it should be, I'm extremely sorry, So it gets added, and what we get is the updated result in the accumulator. So similarly, if we talk about ACI here, we will be including the carry. So again, before the execution, we can see the content is 08, which has been provided with the instruction itself, and previously if the carry flag was having 01, so 01 gets added with the previous content of accumulator, which is 02, and then the data which has been provided immediately with the instruction, which is 08. Everything is in hex. Please remember, whatever we are discussing here is in hex, so the result will also be in hex. So what happens is, when this gets added, it becomes 11. So 11 is nothing but 0b, which comes after a. So 9 is 9 in hex is 9, and then if we treat 10 is 0a, and 11 is 0b. So what the result here is 0b, and it is saved in accumulator itself. Now let's have a look at double addition. Now when we talk about double addition, the usual mnemonics is given by DAD RP. So one of the example, DAD RP here, DAD RP means we are considering the register pair, and you have to remember one thing: whenever we are considering DAD, the by default register here is HL. Now let's see, if we take an example which is DAD H. DAD H means the content of HL gets added with content of HL itself, and it is saved in HL. So suppose before execution we have a content which is shown here. Now on the right hand side you can see it is 82. Again, it is in hex notation. We have written it in hex notation. It's understood that we are writing and showing this in hex notation. And on the left hand side we have H. The H register is having 02, and similarly, so if we try to execute this particular instruction, the same content gets added with the same content in HL. So if we see the after execution, it will get added like this. The content becomes 0, now carry 1, and similarly this gets added, it gets added, and now since there will be a carry, you can see a carry is transferred to the next, and it gets added and stored in H, and similarly it goes on till the addition is complete. Okay, so you have to remember one thing: whenever we are going with DAD, that is the double addition, in this case the lower portion which is stored in L, when gets added, it may transfer a carry to the higher byte which is usually stored in H. In this case, HL register pair is the by default register pair. So again, there can be another possibility, that is DAD RP. Here we are considering DAD B. So the content of HL now gets added with content of B and C, and it is saved in HL. So again it is the same thing, it gets added in the similar manner, and if there is a carry, it will be reflected in the flag, and then again it goes on until it gets completed. Okay. Anujit, please switch off your microphone. Okay, fine. Now let's move on to the another example, which is DAD D. Here again the HL is getting added with DE. The result is in HL. The similar technique is carried out, and if there is any carry, it will get reflected in the carry flag as shown in the figure, and goes on till it is finished. Okay, so the result is stored in again in HL, but in this case it was added with DE register pair. Here the DE register pair are done simultaneously, so even if there is a carry at the lower portion, it will get reflected in the carry flag. Now let's move on with the sub operation. In the sub operation, that is the subtraction operation, it is similar to addition operation, but internally this is carried out by the microprocessor in 2's complement method. So in this case again will be subtraction between the CPU registers. So here again we have the accumulator as the default. You can see sub A here, it means again subtracting the content of accumulator from the accumulator and reflecting in accumulator itself. So there are other instructions like sub B, then we have sub C, then we have sub D, then we have sub E, and again we have sub H, and again we have sub L. In every case that has been considered here is the content of accumulator is getting reduced by the content of the other register. That means here if it is 06, this one 03 in register B, 03 gets subtracted from A, not the other way around. Okay, so it is always accumulator on the higher side and the other one on the lower side. So any content which is provided in the other register gets subtracted from the content of the accumulator. Now let's move on to sub M. Again it is similar. We are talking about register indirect addressing. Here before the execution we can see that the HL is pointing towards 000 E000. So the content 02 will now get subtracted from the accumulator and it will be reflected in the accumulator itself. So in case of sub M, always it is relating to memory. Whenever it is relating to memory, it is relating to HL. Okay, now let's move on to SBB. Here the content of the register mentioned in the instruction is subtracted from accumulator along with the borrow immediately and saved in accumulator itself. Here the default register again is accumulator. So if we consider an example, here you can see the content of accumulator is getting subtracted by the content of accumulator and the borrow itself. So what we get here is the result in the accumulator after execution. So again there is another expression which is given here as SBB. Here the content of register B is subtracted from the register A along with the borrow. So we get the results in the similar fashion. So this was the example of subtraction, and I have only shown you 3. There are others also, but it is the same way it functions. Now let us talk about SBBM. Again here we are considering the accumulator content with the memory content and the borrow. So the content of the memory gets subtracted from accumulator and the borrow under consideration. So we get the content in the accumulator itself. Now if we talk about SUI, now the subtraction comes under the immediate addressing mode, where before execution if we try to consider, we were having a content in accumulator which is 0E, and after the subtraction it is 08. This is given by a plus sign, but actually this means we are operating on 2's complement way. So that is why it has been given as a plus sign. So if you get confused, you can consider this as a negative sign for simplicity's sake. In the earlier at the beginning of this particular lecture I told you that subtraction will be carried out internally using 2's complement method, where the subtraction is carried out in addition method. Hence I have shown it in this manner. But if you feel that you are getting confused, you can consider this as negative. Okay, so if we talk about SBI, here again we are considering the addressing mode immediate addressing mode, where the content will be subtracted from the data immediately provided with the borrow. Okay, so here I've considered a negative symbol for your for the understanding sake. So always remember, the microprocessor which is doing this particular function will subtract everything using 2's complement method. So in this particular section we have seen that the SBI is what it is. It is subtract immediately with the content. So we have the content in accumulator subtracted by the content provided immediately in the instruction, and considering the borrow or the carry itself. In 8085 there is no flag called borrow flag. We will consider the carry flag as the borrow flag. Okay, so whatever is there in the carry flag, that will be subtracted. So in case of all subtraction operation involving borrow, the carry flag will be treated. So this is a very important understanding, since we do not have any flag specially for reflecting borrow. Okay, so this is the end of today's lecture.